So, thank you for the nice introduction. And the agenda is short, we only have half an hour. So, the first point is ultra-low superheat. Just a short explanation of what that is and what we can use it for. And then I have a little bit on injectors, low pressure lift injectors, high pressure lift injectors, and where can we use that, what can we use it for, and so on. So, first of all, ultra-low superheat is basically just reducing the superheat in the evaporators, and the benefits we get from that is we get lower density of our evaporators. As a consequence, we can raise the suction pressure of the rack, the compressors, and therefore we can get an energy saving out of that. Downside to it is that when we lower the superheat, we also get liquid back from the evaporators. And that we need to handle somehow. We can either do it with a pump, we can evaporate the liquid, or we can use an injector to remove the liquid. That's basically three options, and there are probably more. Just a very simple design with 4 evaporators in this case. One of the important things is, first of all, we of course need to lower the superheat, otherwise we won't get the benefits. But to harvest the benefits, we also need to run modulating thermostat. So that basically means that some of the evaporators are running on superheat control, but the others are the ones that are not so loaded. They're basically running with temperature as set point for the valve. And then to increase the suction pressure or higher that, we also need to run pure optimization. So that's basically the 3 control issues that we need to use. So if we take a normal evaporator with direct expansion, you can see that the most loaded evaporator is the one where we have the smallest temperature difference. And the temperature difference is basically between ingoing air to the evaporator and outgoing CO2. If we can decrease the superheat, then we can also move this lowest superheat or lowest temperature difference, we can move that to the other end of the evaporator. And by moving it to the other end of the evaporator, then that basically means that we can run higher suction pressure because we have more temperature difference available. So then suddenly it looks like this. So that's basically what ultra-low superheat is all about. If we combine the 2 scenarios, then you can see that typically we raise the evaporation pressure by something like 5 Kelvin in average. And that gives us an energy saving that is approximately 10-12%. Of course, you can do this on CO2, but you could basically also do the same on HFCs. On CO2, we have some, let's say, some other handles we can pull. We have ejectors and so on, and they are more efficient on CO2 systems and HFC systems. So that's why it's coming up now. But basically, there's no reason why we could not do this in HFC. So, I will not bore you with a lot of test data, but we did some tests in a cash and carry supermarket in Germany. 220 kilowatt empty load, and we only have ultra-low superheat on the empty side. We can also do this on LT, but in this case we only did it here. And it has been in operation for a little bit more than 2 years now. So what we did was we ran 1 week with low superheat. We ran 1 week with 3 Kelvin, which is also pretty low. And then we ran 1 week with 6 Kelvin. And then we repeated that 3 times. So basically, if we should boil that down, then this graph here actually shows the results of the 3 weeks. So ultra low superheat, that is what we say that is 1 Kelvin superheat. There you can see we have a evaporation temperature on the y-axis that is around minus 1.8, something like that. 3 Kelvin, you will see we have a temperature or an evaporation temperature that is a little bit lower than minus 3. And if we do 6 Kelvin, which on CO2 is actually also in the lower end of what we would normally see. Normally we see something by, let's say, 6 to 10 Kelvin superheat. Then you can see the evaporation temperature is below minus 6. So there's definitely a good match between superheat and evaporation temperature. Then the question is, what does this actually, what saving does that give us? If we say that we cannot do better than 1 Kelvin superheat, that's the lowest superheat we can actually run with, then we could say that there we have a temperature penalty of 0 Kelvin. We cannot do it any better, so this is the best we can achieve. If we run 3 Kelvin superheat, then suddenly we have a temperature penalty on our evaporation temperature that is around 1.5 Kelvin, and 6 Kelvin superheat we have a temperature penalty that is roughly 4.5 Kelvin. And we know if we use 2.5 Kelvin or 2.5% energy saving per Kelvin, then you can see the energy penalty that we are paying for the superheat that you can see on the secondary y-axis. So typically going from 6 Kelvin down to low superheat will give you something like 10-12%. Yeah, that's for the MT part, but the LT part is usually smaller. But if you apply the same principles on LT, you'll get to see the same savings. So basically, I think that the saving on ultra-low superheat is actually quite well documented in this study at least. And in this case here, we are using Danfoss liquid injectors, and we have in the test period, we have not seen any problems with actually pumping the liquid back. The highest liquid level we have seen in the suction accumulator is 7% liquid, which is not in any way frightening. One of the other things we actually see is that typically the evaporators that we have a difficulty controlling, which is usually the ends of gondolas and stuff like that, when we use ultra-low superheat, they're actually a lot easier to control. So they're usually not the ones showing up as the most common case. So that's also one of the interesting things is that suddenly the problematic ones, they're not so problematic anymore. Yeah, so that's it on the German side. Then on the bigger racks, as the one in Germany here, we are using liquid injectors, as I said. But on the smaller racks, up to 100, 130 kilowatts, we use our special receiver design, where in the bottom of the receiver here, we have a coil. And this coil is big enough to evaporate all the liquid that we have coming back from the evaporators at low temperature. We have a temperature difference here of something like 25 Kelvin. So that means this coil here can actually take typically up to around 30% liquid returning from the cases, and we are far away from that when we use the ultra-low superheat. And on the medium temperature, we have a vessel inside the receiver. So that means the gas and liquid coming home to the rack from the empty evaporators is the liquid part is basically captured in the vessel. And since the vessel is hanging in CO2 that is, let's say, 10 Kelvin warmer, then the CO2 that is left, the liquid that is left, is basically being evaporated. So on smaller systems, we are not using the injector, and we are using simple to evaporate the liquid. This is actually proven quite useful. So in Norway, we have a small supermarket running minus 25 evaporation on low temperature and minus 0.4 evaporation on empty. So quite high suction pressures achieved in this study. So enough about low superheat, but there's a potential saving here. Usually we say that it's around 10%, and then my contractors, they say that 10%, that's not enough. It's more than that, but it is in that one. If you look at the payback time on the smaller ones, you can see the saving here is around 10%, and here it really doesn't matter where we are placed, because this is an evaporator thing. It has nothing to do with the ambient. So the saving, no matter where we put it, is basically the same. Payback time on the small racks, since we're using this receiver construction, which is standard, then we're not having any extra cost on it. If we move to bigger racks, you can see it's 200 kilowatts. Then you can see we get paybacks in the order of, let's say, 2 to 4 years, depending on where we are. And it is, the difference in payback is because it is basically more expensive to operate the refrigeration system in Athens than it is in Norway. So therefore there's a little bit more to do the payback with in these. So then a little bit about ejector systems. The basic cycle we are normally using is a simple booster system where we have LT and MT compressors, we have LT and MT evaporators, we have the gas cooler, and out of the gas cooler we do the first throttling in a high pressure valve. In the receiver, we of course store our liquid, but we also use it as a separator, so we separate gas and liquid. On a warm day, approximately 50% of the flow coming into the receiver is gas. That we send through the gas bypass valve directly into the compressors. So that means that we have the gas in the receiver at something like 40 bar, and then we throttle it down to something like 25 bar, just to put it into a compressor again. That's not always very smart, but it's. So of course we can use this to enhance our process. So if we do high pressure lift applications, then that means when we do high pressure lift injectors, we are also using parallel compressors. And in summertime, the parallel compressor is basically substituting the gas bypass valve. So in winter time, the system is running like that. There's no flow to the ejector. There's no flow through the parallel compressor because the gas fraction coming down from the gas cooler is very low. So then we're basically back to the standard booster system. In summer mode, suddenly there's more energy available for the ejector. That means that the ejector starts to pump. And we are approximately taking 50% of the gas going to the empty compressor. We are approximately taking 50% of that, putting it through the ejector. Then it lands up in the receiver, where the parallel compressor is taking it. So instead of having, let's say, having the empty compressors to do all of the mass flow, then in this case the parallel compressors are actually doing around 75% of the flow. And since they're working at a higher suction pressure, it actually gives us a quite nice saving. So again, it of course all ends up with savings and payback time and stuff like that. So the two numbers you can see in the seasonal energy performance, that is the first one is the COP of a traditional booster, and the second one is the seasonal energy performance for a system with ejector. And you can see in Norway is a cold country. The savings are very big because there's not a lot of fuel for the ejector. So 5% saving here, and the payback time here is around 20 years. And that is if we do a 70 kilowatt system. If we go to Athens, well, yes, maybe here it is a little bit more interesting. The saving is a little bit bigger, and the payback time is shorter. But where this principle actually really makes sense is if we take it to a larger system, a 200 kilowatt system, for instance. Savings in percent is the same, but suddenly it makes sense to actually do this. It makes sense because parallel compression alone is a very expensive technology to utilize, and we need parallel compression for the high pressure lift detectors. So we basically need to have a certain size of it. The starting cost of doing parallel compression is pretty high. So that's basically the thing about high pressure lift detectors. So the conclusion on that part is probably that on smaller systems, high pressure lift detectors is not the technology to look for, but on larger systems it's actually making good sense if you are, let's say, a little bit warmer climate. The high pressure lift detectors, they have been around for 3-4 years now. But as you can see, we have a gap on smaller systems where we basically do not have a technology that can bring us down into warmer climates because we are somehow stuck with booster technology. We cannot use parallel compression because it's too expensive. We cannot use high pressure lift detectors because that is also too expensive. So we need something else here. And this something else could be a low pressure lift detector that we are basically doing quite a lot of testing on at the moment. Yeah. So how the system works, you can see here. In winter time, it's basically just a normal booster system, like the previous system. When we go into a warmer ambient, then the ejector we are using here, it cannot give a high pressure lift like the previous one, but the pressure lift is lower, but it's basically giving us a much higher mass flow. So instead of taking half of the flow coming from the evaporators, then this ejector here can actually take the full flow coming from the evaporators. And then it's lifting the flow from the evaporators through the ejector to the receiver, where the compressor, and now we don't have a parallel compressor anymore, now we only have a medium temperature compressor that is basically running as a parallel compressor here, you can see. But that means we do not need two suction groups, we do not need extra controls for parallel compression. At the end of the day, the system here is actually a lot simpler than the system with parallel compression. So taking that into an environment like Greece, for instance, it would be a lot cheaper. The saving, on the other hand, is not as big. You can see if you go to Athens, I think we have around 14-15% before with the high pressure lift detector. Here we are down to approximately half. But the question is, on smaller systems, isn't that actually good enough? Because it brings us the saving we basically need to come down here in the warm ambient to have a same or better efficiency than the HFC systems, and without a huge extra cost. So you can see if we are in a warmer climate, then the payback time around, let's say, 2 years is actually okay. And that is on the small systems. On the larger systems, the payback time is even shorter. But there are maybe some technical aspects that makes it not so attractive on the larger systems, because the low pressure lift detector cannot give us such a high pressure difference, and that means we don't have so much temperature or pressure difference to force the liquid through the system into the evaporators and back again through the suction line. So there's probably a limit on how big systems we can do, because bigger systems they usually have longer suction lines and stuff like that. So here there is a boundary on the low pressure lift ejector systems. But for, let's say, smaller supermarkets up to maybe 150 kilowatts, this could actually be a very nice technology to apply. So, when to use what? I believe, and this is, let's say, something that we need to go and improve, because the high pressure lift ejector we have good experience with. The low pressure lift ejector is something that is relatively new to everybody. But I believe that high pressure lift ejectors, that is for larger systems, are now, I say, 100 kilowatts plus. If that's 100 or 150 or 200, I don't know, but it's basically for a little bit bigger systems. And the low pressure lift ejector could be for something like from 20 kilowatts up to 100 kilowatts, 150 maybe. We see quite attractive paybacks if we are in warm climates, and even in a cold northern climate, if we can combine it with heat recovery, it makes very, very good sense as well. And then the payback time for the low pressure lift ejector looks even better than the high pressure lift ejector. Just remember that the saving from the high pressure lift ejector is actually twice as big. So if you have, let's say, a system of a certain size, it's basically creating a bigger revenue for you. So that's also important to keep in mind. Then the good thing about these savings, if we should sum up, is that there's no reason why we should not be able to run with both high pressure lift ejectors and ultra-low superheat at the same time. It's two different technologies. It's two different places we get the saving from. So here we can basically combine the savings. So that means if we combine a high pressure lift ejector with ultra-low superheat on the evaporators, then we basically get a total energy saving around 25% compared to a standard booster system. And we get a payback in the order of, let's say, 1.9, let's say 2 years. So basically that is, that's what I prepared for you today. Any questions?
For the ultra-low superheat, how do we achieve it?
How do we achieve that?
Just set the controller to be at one superheat, or?
That is a little bit different from control manufacturer to control manufacturer. Now, I was developing this system when I was at Advansor, so I can pretty much in details describe how Advansor is doing it, but how the others are doing it, I don't have that deep knowledge to. But the way Advansor is doing it is that they basically have two sets of set points in the controller. One set point is for 1 kilo superheat without basically any safety. So that means that they allow the controller to go below the 1 Kelvin without throwing the emergency brake or anything like that. And if there's something on the rack telling that we are not able to remove the liquid, then they send a signal to the controller to switch back to a second set point where they have a higher superheat and where they also have all the safety functions. So that's the Danfoss way of doing it. But Corello and the others, they have something similar. I'm not that much into details.
So the extra cost of this is the pump or the injector to circulate the liquid?
You need a suction accumulator, and we need some kind of pump to remove the liquid. Where the ejector could be one possibility.
And the second is your present are compared to what? To standard
Booster. Yeah.
And in comparison to an HFC system, for example, how does it compare?
I would say that the ejector alone would make us able to compete no matter where we are in the world with HFCs on energy consumption. If we are talking on annual basis. And I think most places we would actually also be able to compete with them in, let's say, hour-to-hour COPs. There are some places where it's awfully hot. When we do racks for Portugal, for instance, it's 44 ambient. And then the efficiency of CO2 is not as high as we would hope for because we have some limitations on pressure. So there we suffer on efficiency when it's 44, but that's only, let's say, 3 days a year. So in the total picture, it really doesn't show up.
And for industrial application, for example, how does it compare with ammonia?
Ammonia is a fantastic refrigerant. And to compete, let's say, one-to-one with ammonia on COP is difficult. It's impossible. But ammonia has some other challenges. We all know that it's toxic and it's also flammable to some extent. And that means that quite often we see these low-charge ammonia systems where you have a brine circuit on the low side and sometimes also have some kind of, let's say, air-cooled or water-cooled condenser. And in that case, if we quite often see it on heat pumps right now in Nordic countries where this is a COP application where you measured very hard on COP. And then we can see we get very, very close to ammonia if you include the brine system on the cold side. But let's say on a one-to-one comparison, ammonia is better. Yes, if we have our flooded systems or whatever, then ammonia is just a fantastic refrigerant.
And one question with low suction, low superheat, do you have any safety issues for the operators?
We have
So for example, the controller you got us has an emergency brake.
yeah, but we also have a suction accumulator, and there we measure the liquid level. And if the liquid level here is too high, then we basically ask the compressor or the evaporators to stop flowing, to go back to high superheat. So that's the safety concept we have. And the controller is also made in a way so that if you actually lose the bus communication, then after 15 minutes it will automatically return to high superheat. So there is some safety. Okay. Yes.
Any other questions? No. Thank you very much for your presentation.